Hi everyone. So for this first question, with all these questions, in fact, what I'd like to do is I'm going to answer them as if you don't know what to do to start with. So at least we can get some marks from the calculation questions using the numbers we've got. So here we've been given a few numbers. We've got 50 centimeters cubed of a 0.8 mole per dm cubed solution of the ammonium vanadate, and it reacts with 506 centimeters cubed of sulfur oxide gas measured at 20 Celsius and 98 kilopascals. So you've kind of got two ways of working out some moles there. We're going to first work out number of moles of the ammonium vanadate. So we've got moles of NH4VO3 equals 50 times 0.8 over 1,000, which gives you 0.04 moles. Now, so I'm not really working out what the question wants me to work out at this point. I'm just working out what I can work out using the numbers I've got in the question. So the next thing I'm going to do is work out number of moles of SO2. And to do that, I'm going to have to use PV equals nRT. So if I just write out PV equals nRT, the reason I know how to use that is because I've been given a pressure, I've been given a temperature, I've been given a volume. Immediately that should shout out to you ideal gas equation. So to work out moles, I've got to divide both sides by RT. So that means I need the pressure, volume, gas constant and temperature. So if I just write those out as I've suggested we should when we're doing an ideal gas equation question, so we've got the right units. So we've got 506 centimetres cubed. So that should be, where's the volume? 506 times 10 to the minus 6 metres cubed, so I've got to divide by a million. I need the temperature, which is 20 Celsius, but I need that in Kelvin, which would be 293 Kelvin, so I've added the 20 to 273. I need the gas constant, which is 8.31, which is given in the question, and I need the pressure, which needs to be in pascals, so I've got to times that 98 kilopascals by 1,000. So I'm going to put all that into my equation, so I've got 98,000 times by the volume, which is 506 times 10 to the minus 6, and divide that by 8.31 multiplied by 293. Make sure you put these in brackets if you're doing it on your calculator all in one go, but I recommend that you do one, then the bottom, and then do one divided by the other, rather than trying to put it all into your calculator in one go, which can lead to mistakes. Now that equals 0.0204. Okay, so the next stage is to go back to our question and look at what we're actually trying to work out, because we've got some marks there for working out number of moles of each of those. So to use this information to calculate the oxidation state of vanadium in the solution after the reduction reaction with sulfur oxide. So what we need to do is work out, essentially, how many electrons have been transferred, because that then will allow us to work out the new oxidation state is. So it tells us that the reduction reaction with sulfur oxide, so if the sulfur oxide is acting as a reducing agent, that means the sulfur oxide is being oxidized itself. And what we should know is that, firstly, in terms of the knowledge we're using, we know that if we reduce sulfuric acid using the halide ions, that goes to either SO2S or H2S. So SO2 is our first kind of reduction product. So if we're going back again, if we're oxidizing from SO2, then we're going to be making the sulfate ion. So SO2, and that's going to create SO4 in this reaction between the ammonium vanadate and the sulfur oxide gas. So then we've just got to balance it so that we've got a half equation. So the sulfurs are balanced, then balance the oxygens with water, so we're going to add 2H2O onto this side. Then we're going to balance the hydrogen, so by adding 4H+, and then we've got to balance the electrons. So on this side, we've got a 0 charge. On this side, we've currently got a 2+ charge. We've got 2- from the sulfate ion and the 4H+, so we've got to add 2 electrons onto this side to make that balanced. So that means we need to work, now we can work out how many moles of electrons were added to the ammonium vanadate. So for every one SO2, I add 2 electrons. And you can see that I've got a certain number of moles here of SO2, which is 0.0204. So the moles of electrons added to the ammonium vanadate will equal 0.0204 times by 2, because the 2-to-1 ratio between the electrons and the sulfur dioxide gas, which equals 0.0408. So if we now look at the ratio of the moles of the ammonium vanadate and the moles of electrons that are added, it's pretty much 1 electron per ammonium vanadate molecule. So that means that the oxidation state is going to just reduce by 1 number. So we've got to now work out the oxidation state of the vanadium in this compound. So oxidation state of V in NH4VO3 is going to equal, so the NH4, we know the ammonium ion is 1+, so we're going to have a plus from all of this, and then we're going to have -6 from the 3 oxygens, so therefore the vanadium must be +5. So this means that if we're adding 1 more electron, then that's going to be +4. So let me just go through that once more from the top. So the first thing we did is work out number of moles of the ammonium vanadate using the numbers in the question. Then we worked out number of moles of the sulfur dioxide gas that was used, and it tells you that that is all reacted completely. Then we worked out how many electrons each sulfur dioxide molecule gave to the ammonium vanadate. We saw that the ratio of the sulfur dioxide and the electrons was 1:2, so we multiplied the number of moles of sulfur dioxide by 2 to work out how many electrons were added. We saw that it was 1 electron per ammonium vanadate molecule, so therefore the oxidation state of the vanadium in the ammonium vanadate is going to just reduce by 1 because there's 1 electron involved.